Suppose you have a data that looks like this, and you want to find the mean value. One way to approach it is just using the formula we all know, which is adding up all the numbers 1 plus 1 plus 1 plus 2 plus 3 plus 3 divided by 6. So that's 11 over 6. Oh, you know what? Let's make it a little bit easier for us. I don't want those ugly fractions everywhere. Okay, so over 5. So that's, right now that's 8 over 5, which is 1.6. And that's our mean value. Well, alright, we wanted the mean value, we found it. But we can go a bit further. So if we look here, we have 3 entries of 1. So I can put it like this, 1 times 3. And then we have only 1 entry of 2 and 1 entry of 3. Still over 5. And then we can separate that fraction. Right? We can write it as a sum of this thing plus this thing and plus this thing. So let's do that. So our x mean is now equal to 1 times 3 over 5 plus 2 times 1 over 5 and plus 3 times 1 over 5. So let me take a step back and look at our data. What if this is the outcomes of some random event? So you can have 1 in 3 different ways, you can have 2, or you can have 3. Then I see that I have 3 outcomes which yield me 1, and I have 5 total outcomes, and that means that probability for 1 is 3 over 5. And using just the same logic, probability for 2 is 1 over 5, and probability for 3 is 1 over 5. So what we have here, these numbers, they are in fact probabilities for corresponding entries. And apparently, to find the mean value, we are taking each entry, multiplying it by its probability, and then adding everything up. And it's not some special lucky coincidence here. It's the general rule. It works everywhere. So we had our old formula for the mean value, which is sum everything and divide by total number. Now we have the new one. So math tells us that you can calculate your mean value in slightly different way using probabilities. You take each entry, you multiply it by corresponding probability, and then you take the sum. And this definition of a mean value is more versatile. There are much more cases when you will use this compared to this, because sometimes you're just not able to use that standard definition we had. And there's more to that. We have the law of large numbers, which tells us that if you have a large data set, then your frequencies, your relative frequencies, will be close to probabilities. So whenever you have a large data set and you don't want to mess with the raw data, or maybe you even don't have the raw data, you can use this. Just substitute frequencies instead of probabilities. We already did that. In fact, we did this same thing when we calculated weighted mean for anything. So when you are calculating weighted mean, you take each entry, you multiply by the frequency, by absolute frequency, and then you divide by the total sum of all the frequencies. But each frequency divided by total will give you the relative frequency. And in case of large data sets, your relative frequency is just your probability, or at least it's very close to your probability. So we can use this when we don't have the raw data. So now I will introduce a data set. It won't be large one, because nobody wants to manually process large data sets. And we will be using it just for illustration, so I will take smaller data set and we will compare what happens if we use the distribution and the frequencies instead of pure raw data. So maybe our data looks something like this. Okay, let me separate it. Maybe we have something like 0.5, 1, another 1, 1.5, 4, 7 and 8. Let it be this. I'll go ahead and calculate the mean value. So for this case it will be, let's do it together in fact, so 8, 15, 19, and these two decimals give us 2, so 21 plus 2, 23, and we have 1, 2, 3, 4, 5, 6, 7 entries. So our mean value, our true mean is 23 over 7, and that's approximately, so it's somewhere around 3.2. That's not exact number, it's close to 3.2. Let me check if we need higher accuracies. Okay, in fact it's more close to 3.3. It's 3.28, 3.29 even. Yeah, alright, let's add. Okay, so that's our true mean. We will go back to it a bit later to compare. So let's say that you don't have that exact data, but you have the frequency distribution. So you know that you have 4 numbers between 0 and 3. So starting with Starting with 0, I should have put more place in there. Sorry. So 0 and 3, and then 3 up to 6, and 6 up to 9. So we know that there are 4 numbers in here, and then we have one number here, one entry, and 2 entries here, but we don't know which exact entries they are. When in fact, let me shift those numbers here, because I will need some space a bit later. Okay, we have our frequencies. I will go ahead and find the total frequency. So it's 7. Now I can find the relative frequencies. 4 over 7 is 0.57. And 1 over 7 is something like 0.15. Okay, 0.14. And 2 over 7 is 0.29. They are rounded up. They are not exact. So what do I do here? How do I calculate my mean value? Well, first thing, we don't know which 4 numbers are there in this interval. And if we have no way of finding out the exact numbers, then we will have to approximate. Here, of course, we have the data itself, and we can say, hey, what are you talking about? We know that they are 0.5, 1, 1, and 1.5. But let's pretend that we don't know this data. We only have this table. So what I will do, I'll find the middle of this interval, the center. And the center is 1.5. And I will say, look, I don't know which 4 numbers we have, but I will assume that we just have 4 1.5s. So I'm assuming that my data looks like this: 1.5, 1.5, 1.5, and another 1.5. And then we have next interval, and its center is 4.5. We know that there is only one number, so I just assume that number is 4.5. And then here we have 2 numbers between 6 and 9, and the center is 7.5. So I'll just assume that we have 2 7.5s. That's nowhere near the data we have, right? In fact, we don't have 4.5 or 7.5 at all. We have 4, and then we have 7 and 8. But if we don't know those exact numbers, our best bet is assuming that it's the center of the interval. And now I will use those centers as my x values. So what I need to do to find my mean value is multiply each of those center points by the relative frequency, and then add them up. Oh, in fact, I didn't even need to shift them up because I won't be dividing by anything, but okay, so we already did that. So 4.5 times 0.14, and then 7.5 times 0.29. What will that give us? So let me calculate. 0.5 times 57, and then 4.5 times 14, and 7.5 times 0.29. It's 3.66. And it's not terribly close to our true mean. There is a difference, and that difference is not very small. It's about around 10%, but we have small data set. We have only 7 entries, as I said, and we did 2, so that led us to 2 computational errors. First, when you have small data sets, your actual entries might be very far from your center point. So when I supposed, for example, that I have 1.5, that all my numbers in first interval are 1.5, it's not necessarily true, and it's not even necessarily accurate, right? Here we're lucky enough, and those numbers are really close to 1.5. However, we have much more that are closer than 1.5. When you have large data set, you will have approximately the same number of entries larger than your center point and smaller than your center point, so when calculating mean, that will even out. But for small data sets, that creates some errors. And then what's more important, we just assumed that our frequencies are probabilities. And we know that for that to be close to truth, we need to have large datasets, very large datasets. Sometimes even a dataset of 1,000 entries will not fulfill that condition. You need tens of thousands of numbers, and we have only 7. So most probably our frequencies are very far from true probabilities. But still, we get something reasonable. And the difference is only 10%. It's not twice as much or thrice as much. We don't get 7 as our mean value. We don't get 1. We get something close to our 3.2, 3.29, I guess. Let me check. Yeah, 3.29. So that method, it's good enough. And when you have large data sets, it's just perfect. Because usually when you have large data sets, you don't have pure raw data. You only have some frequency tables or distributions like this. As we already see so on the lesson, yeah, the statistical committee does not provide pure data for ages. They only provide age groups. So the only way you can calculate your mean value or something other is this. Okay, that's good. Another thing. Variance. So, variance is just the sum of deviations squared divided by the total number, minus 1. What I want to do is, so I will denote these deviations by delta x. That's the standard notation, so if you see delta x anywhere, it's just the deviation of x. I will divide by n, by total number, and multiply by it. So nothing changes because they cancel out. But now I can treat this part as just the mean of the squared deviation multiplied by this thing. Now, if we have large data set, if our n is large, let's say for example that n is 1,000, then this thing n divided by n minus 1 will be very close to 1. So just using this example, if n is 1,000, then 1000 divided by 999 is 1.001001 and so on. So it's very close to 1. So when you have large data sets, you can remember, you can just forget about that -1. You can just take the mean of your squared deviations. And as we already know, for large data sets, we can use our frequencies for finding the mean. So that leads us to this thing. Variance is just, we take each squared deviation and we multiply by corresponding probability, and then we add them up. So again, that's for large data sets. So if you are working with big data or something like that, this thing will be useful. For smaller ones, it's not so good, but it's still somewhere close. Okay. Oh, and yeah, you can of course substitute probabilities by frequencies. Those two are in fact the only things we need for now. So let me just reintroduce those formulas. So if you want to find the mean of something, you take that something, each entry in it, and multiply by the probability, and then add up. If you want to find the variance, you just take squared deviation for each entry. Okay, I was using k, right? And multiply by corresponding probability and then add up. And there's another thing, another way of finding your variance. So you just take the mean of the squares and you subtract square of the mean from that. So you can either go through deviations and so on, or you can use this and you will get the same result or almost the same result. Okay, so these three formulas is what we need, what we will use, and I will stop at that. The next part we will look at binomial distribution, and then we will have another discrete distribution on Thursday, which is Poisson distribution. Those two are connected, you will see that when we will move to that. But that's all for now. Okay, thanks, bye.